In today's experiment, we are going to use F1-12 from Armfield to calculate the magnitude and the location of hydrostatic force on a plane surface. So let's get started. Now let's talk about different components of this apparatus over here. So we have a tank, obviously, and this is the tank, a plexiglass tank, and the orange wooden piece is a quadrant. You're going to pour water inside this tank, and as the level of water is going to rise in this tank, it's going to go higher and higher, and as a result of water, there's going to be a hydrostatic force acting on this plane surface right over here. You can note the depth of immersion using this scale that we have over here, and the units of the scale is in millimeters. All right, so the quadrant is pinned into a lever right over here. The left-hand side of the lever is attached to a weight pan. Right now you can see I have a lot of weights on top of it. We can put it right over here, and as you put it over here, this is not leveled anymore, right? So then you want to change the location of, or spin this counterbalance to make sure that this lever is again balanced. How do I know if it's balanced? So you can see that there are three lines over here. Whenever the bottom edge of this level is parallel to the middle line, you know that the system is level, and you go ahead and you read the depth of immersion, and also you read the amount of weight, the mass that you have on top of your weight pan. And you're going to repeat this process for partially submerged whenever the depth of water is below this point over here, and also fully submerged whenever the depth of water is higher than this. Okay, so we're going to go ahead and do this process and come back and show you the table of results that we have and how we can process the results to figure out the magnitude of hydrostatic force and the location or the position of action of hydrostatic force. Now that we have done the experiment, it's time to talk about the equations and how we are going to derive the equation for the force and the location of hydrostatic force. So this specific example, this specific slide is talking about partially submerged, meaning that this is the level of water right over here that I'm showing to you. So the water surface is over here, and this is the face of the vertical plane that we want to calculate the force on. Okay, as you can see, it's partially submerged. It's not fully submerged. All right. So first of all, we need to write the hydrostatic equation, and the hydrostatic equation is gamma of water in our case, cross-sectional area of that vertical plane. H bar is the distance to the center of gravity, and the center of gravity is located right over here. Okay. So in order to calculate F, we need to calculate cross-sectional area. Also, we need to calculate H bar as well. Both of these tasks should be pretty easy. So, cross-sectional area, we want to find the cross-sectional area of this flat vertical plane that is submerged underwater. So, essentially, we are looking for in this area. And to calculate that area, we just need to have capital B times D. And the next thing that we want to calculate is H bar. H bar is the distance from the surface of water to the centroid. So in this example, this H over here, this is equal to our H bar. And we can write that in terms of d. And d is the distance from the surface of water, right over here, all the way, right over here, all the way to the bottom, right over here. So we can write this h bar in terms of d to the power 2, because we know that the center of gravity is going to be right in the middle of that distance d. Okay, now I can rewrite the equation for hydrostatic force. And I can, instead of gamma, I can write rho times g. Rho is density and g is the acceleration due to gravity. And what I will have after some simplifying, okay, so this would be the equation that I will use to calculate force when I have partially submerged condition. Okay, now we can calculate the distance from the knife edge, and whenever I say knife edge, I mean this area over here. Okay, I want to calculate the distance from the knife edge all the way to the location that the force is going to be applied. And I know that my force is going to be applied to center of pressure. So here on this figure, I want to calculate this distance from my experiment and call it experimental value. And let's call this distance h double prime. Okay, h double prime, I want to find it experimentally first, and then I want to compare that to the theoretical value. Okay, so let's find experimental h prime. H double prime, excuse me. In order to do that, the easiest way is to calculate the moments about the knife edge, the moments of all forces about the knife edge. So we have one force over here, that's our hydrostatic force. We have another force right over here, and this force is as a result of the mass that we put on top of the weight band. We do have the value, the length from this force to the knife edge. This length is L, and h double prime is the distance from F, hydrostatic force, to the knife edge as well. So what I'm going to write is, let's consider this direction to be the positive moment direction, and I'm going to calculate the summation of moments about the knife edge. This should be equal to 0 because the system is in equilibrium. All right, so the first force that I can write the moment of is F. The distance to the knife edge is going to be h double prime. So moment is force times distance. And the other one, which has the negative sign, would be mg. That's the weight times the distance to the knife edge is L, as I showed you. This should be equal to 0. So I can rewrite this equation to be F times h double prime is equal to mg L. All right, so my goal was to find h double prime. So h double prime can be easily calculated using this equation. And in this equation, we call it experimental h double prime because I do have all the values. I have the value of mass from the experiment. G is known. L is measured and given to you, and F is also calculated using this equation right over here. So I do have all these values. All right, so this was our experimental h double prime based on the experiment that we did. Now, theory also gives you another equation for h double prime as well. What do I mean by that? So our next objective is to find the theoretical h double prime. So I know that if I want to show you that flat surface, it would be something like this. I know that hydrostatic forces on this flat surface are going to be triangular. In other words, I am going to have, so the level of, if the level of water is right over here, the hydrostatic pressure over here is going to be nothing, 0, and the hydrostatic pressure over here is going to be something like this. So the hydrostatic distribution on this surface is going to be triangular. whenever you have a triangular hydrostatic distribution, and let's add all the distances that we know. This is going to be d, and the force is going to be acting in this direction. So this is going to be force somewhere over here. Okay, so whenever you have a triangular hydrostatic distribution, we can easily find the location that the force is going to be applied to or acting on. That location can be measured from the bottom, can be measured from the top of this triangular. If I'm measuring it from the bottom, in other words, if I'm measuring this distance over here, this distance is going to be 1/3 of the height of that triangle, which is d. If I'm measuring it from the top, obviously it's going to be what? It's going to be 2/3 of the height of the triangle. Okay, so in other words, if I want to find h double prime from theory, take a look at capital H value, and capital H is right over here. Okay, this is capital H. I want to find h double prime, so I can say h minus d divided by 3, which is this value over here, gives me d double prime. So essentially, this distance over here is going to be d divided by 3. So capital H minus d divided by 3 will give me h double prime theoretically. All right, now we are going to, and obviously this one is the value of h double prime experimentally. We are going to compare these two values in an Excel sheet to see if our experiment is accurate or no. This was one of the objectives of this experiment, right? To compare the values of these h double prime. These values represents the distance from the knife edge to the center of pressure. If these two are close to each other, it means our calculated center of pressure is close to the theoretical center of pressure based on the equations. Now let's move to the next slide and do the same thing for fully submerged condition. All right, now we are going to calculate the same equations, but this time for fully submerged vertical plane. As you can see, the level of water, which is right over here, is on top of this surface that we are calculating force on. The equations are exactly the same thing. For example, the force can be calculated using the same familiar hydrostatic equation, and this time the only thing that would be different, I'm going to write area, which is capital B times capital D. So this would be this area this time, and because it's fully submerged, we are going to use capital D times capital B, and then h bar is going to be D minus capital D divided by 2. Obviously the center of gravity is right in the middle of it, and right in the middle of this would be capital D to the divided by 2, and then D is the distance from the surface of water all the way to bottom of this flat vertical plane. Okay, so this would be your force. Now similarly, we are going to calculate experimental h double prime. And similarly, you need to write down the summation of the moments around knife edge, and that should be equal to 0. And if you write it again, you are going to reach out the same equation, exactly the same as previous slide. The only difference would be that this time F that is here should be calculated using this equation. That's the only difference from the previous slide. And then we are going to go ahead and calculate a theoretical h double prime as well. Alright, so in order to calculate theoretical h double prime, first we need to find what would be h double prime parametrically using stuff that we have over here. So let's consider this similar to the previous slide. Let's consider this distance to be capital H. Okay, so and then this distance over here is essentially center of pressure. h prime. H prime is the distance from the surface of water all the way to the center of pressure, which is right over here where F is applied to. Okay. Now, I'm going to write H double prime in terms of H prime, capital H, and D. Okay. So I can write H prime plus capital H minus D. Let's think about it. So H prime is the green indication right over here, and capital H minus D, capital H is the purple line, and D is little d is this distance over here. So that, if you look at it, that gives me H double prime right over here. Okay, now the problem is that we don't know how to calculate H prime. Well, we know that H prime is center of pressure. So center of pressure is H prime. And if you have watched my videos related to hydrostatic forces, you know that when you want to calculate center of pressure, you're going to use this familiar equation, which gives you H, and H is, in this case, right over here, is the distance from the top of the plate to the centroid, plus you are going to have I bar, which is the first moment of inertia, H times A. Okay, and let's write this value. This is D minus D to the power 2. Okay, one thing that I want to show you over here, this H should be H bar, because this should be the distance from the surface of water all the way to the centroid. So this is H bar. Okay, and H bar is equal to D minus capital D divided by 2 plus, I'm going to write the fraction. If you take a look at your textbook, you can find the value of I bar from your textbook. For a rectangular plate that I have, it's 1/12 B as its width times capital D to the power 3. And this is divided by H bar times area, which is capital B times capital D. All right, if you do some simplification over here, H bar will be eventually this fraction. Okay, so this was H bar, and I have these two, so I can add it and write my theoretical H prime over here. So H prime is H bar, which was the fraction that I just wrote in green, plus H minus D. All right, and that's the theoretical value of H double prime. You need to compare this theoretical H double prime with the experimental H double prime, and we're going to go to Excel, and I will show you how you can do this. Okay, now we are in Excel. I have created a table, and I have entered the mass that we measured during the experiment and the depth of immersion that we have also measured during the experiment. We want to calculate hydrostatic force, and then theoretical H prime and experimental, theoretical H double prime and experimental H double prime, and calculate the error. So the yellow cells that I have noted, actually noted right over here, these are the yellow region, represents the partially submerged. So we're going to use the equations for the partially submerged, and the blue area over here represents fully submerged. So we are going to use the equations for fully submerged. And this table gives you the information that you need to put in this equation, and we measured this during the lab to be able to calculate all the variables over here. All right, so I'm going to start with force, and because this is partially submerged, I'm going to use this equation for force. Notice that these numbers over here are in millimeters, so when I'm writing them in the cell, I need to convert that to meters as well. Okay, so for force, for example, I'm going to write it and then fast forward it. Density is 1,000 kilograms divided by cubic meters, G 9.81 times B divided by 2 times D to the power 2 right over here. Okay, so capital B is 75 millimeters, and 75 millimeters is 0.075 meters times D to the power 2. D is the depth of immersion right over here, so D to the power of 2, and then the entire thing should be divided by 2, or we can write it as multiplied by half. Okay, so this would be the hydrostatic force for this row of data when you have the mass this much. And now I want to drag this down to calculate it for other rows as well. Okay, now that you have calculated this hydrostatic force, for here we need to switch to this equation right there. I've already written this equation just to save some time. This equation is exactly what's been written over here, so I'm going to press enter and then drag this down, and that would be hydrostatic force for fully submerged condition. Now we need to talk about the theoretical H double prime, and this is the theoretical H double prime for partially submerged. Okay, let's write it down. Is equal to capital H is 200 millimeters, so 0.2 meters, minus D is this cell over here divided by 3. There we go. So this is theoretical H double prime. And in order to calculate theoretical H double prime for fully submerged condition, we need to use this equation. And again, I have written that equation right over here already. Just going to press enter and drag it down. Next, I want to calculate experimental H double prime for partially submerged body, which is going to be this equation. I have written the equation. And this equation has force in the denominator. You can see that I have referred to force over here, and calculate this by dragging it down. And lastly, I want to calculate experimental H double prime for fully submerged body, which would be this equation, and this is the equation for that. I'm going to drag it down. Perfect. And eventually I want to calculate the absolute error. So absolute error, I'm going to use ABS function in Excel. ABS, that calculates the absolute difference between theoretical minus experimental, and enter. Perfect. And this would be, I can change this to blue to make sure, there we go. Okay, so you can see that the absolute error is very, very small. That means that our experiment was fairly accurate. Now let's do some graphs together. The first graph that I want to show you is going to be depth of immersion as my x-axis and hydrostatic force as y-axis, to see how depth of immersion will change the force. As you can see, the force is increasing as the depth of immersion is increasing as well. It totally makes sense. But let's take a look at this graph over here. Perfect. So over here, I'm going to make it smaller a little bit. There we go. And let's add the axis title over here. So for your x-axis, you have depth of immersion right over here. And for your y-axis, you have hydrostatic force. Obviously, as you can see, it's almost linear. You are tempted to say linear, but it's not fully linear. Take a look at this area over here. After some point, and if you want to be like after this point is the last point of your partially submerged. After this point, you can see that the slope of the line changes. Okay, so this is the first graph that I wanted to show you. You can see that as depth of immersion is increasing, the hydrostatic force is also increasing as well. Okay, and then the next graph that I want to show you, we want to compare our theoretical and experimental H double prime. So I'm going to select these two. On x-axis would be theoretical, and on y-axis would be experimental H double prime. This time I'm going to do a scatter plot like this. There we go. Okay, and let's make it smaller so it's easier to, there we go. Perfect. I'm going to make both x-axis and y-axis to same limits. So I'm going to double click on the x-axis and go to axis options and change the limit from 0.19 to 0.195 to match the y-axis, and print and enter and change this to 0 again. Actually not 0, because this is 0.155, so I'm going to change it to 0.155. There we go. Okay. Now you can see actually the data over here. If you want to actually present this a little bit better, you can double click on any of these points and add a trend line. And we want to add a linear trend line and show the equation on the chart as well. You can see that this line is very close to a straight line. Why? Because look at the intercept. The intercept is very small, very close to 0. And the slope of the line is very close to 1 as well. So very close to the bisector of this. Perfect. So now you can see that although there is a difference between the theoretical value and experimental value, the absolute error that we measured is very small. Also, you can observe that from the line that we have over here too. Again, I forgot to add the axis over here, but it's always a good practice and professional to add the axis titles to make sure that whenever you're interpreting this data, you have the axis options, axis labels too. All right, so in this experiment, I showed you how you can calculate the hydrostatic force as a result of water right behind a flat vertical surface, and then we came to Excel and calculated the theoretical and experimental H double prime, which is the distance from the knife edge to the center of pressure.